G'day, everyone. Welcome to Lubrication Experts. I've got a very exciting episode today. Dr. Ian Taylor with us, a visiting professor at University of Lancashire. Very excited to talk about energy efficient lubricants, or the relationship between lubricants and energy use and energy efficiency. I think this is really topical. Obviously, there's a lot of discussion around sustainability, COP27 just having finished as well. All kinds of discussion about new EV drivetrains and things like that. A recent STLE conference about that. But I think this is something that's getting a lot more focus, is the link between lubricants, energy efficiency, sustainability. And who better to talk to than Dr. Ian Taylor, who's done a lot of research in this area. Just a bit of background as well. Dr. Taylor also has a very long history at Shell, where he worked in the technology group for about 30 years there. And so some of that experience may certainly come to the fore during this discussion. So Dr. Taylor, thanks so much for joining us.
Well, thanks for inviting me. I'm looking forward to the discussion.
Yeah, excellent. So maybe just to kind of level set a little bit from the outset, to give us an idea of like what's the size of the prize that we're talking about here. I've seen numbers thrown out from various research papers that indicate, let's say it's in that sort of like 23 to 25% of global energy production is kind of lost in some sense due to friction. So it doesn't go into useful work. It's just expended through friction. Now, obviously, we're not going to eliminate 100% of that. But what are some of the numbers that you've seen, and what do we think is like the size of the prize?
Yeah, there's been quite a few studies over the years on how important tribology is. Tribology is the subject of, friction, lubrication, and wear. And the various studies in various countries like the UK in the 60s, there's been a recent study in China about 2007. Other countries have also looked at this. They reckon that about 20% of a country's gross domestic product is spent overcoming friction. And a more recent study, which was published a couple of years ago by Erdemir, suggested that 3% of GDP is spent overcoming wear. So if you add friction and wear together, it's probably 23%. And so a figure of 20 to 30% is about right. And if you think of the numbers for the UK where I'm based, the gross domestic product is over $2 trillion. So 30% of that is, $600 or $700 billion. So most of the money that's spent overcoming friction is energy costs. So when you drive a car, you fill it up with petrol, and you use petrol as you drive, and very little of that petrol is actually going to move the car. Most of it is overcoming inefficiencies or friction. So as soon as you put petrol in the car and you burn it, only 40% of the energy content of the gasoline gets to the rest of the car. 60% is already lost as heat and noise just through the inefficiency of the combustion engine. And all that 40% that is available from the engine, that some of that is lost as friction internally in the engine, and some of it is lost as friction internally in the gears. And then when the friction gets to the wheels, the car itself has to overcome friction losses like the aerodynamic losses, the wind resistance, and the tire rolling resistance losses. So when people have looked into this, if you look at the energy content of the gasoline, there's only about 10% of that energy actually gets to the wheels and enables you to actually accelerate and drive. Most of the rest is spent overcoming either inefficiencies or friction. And if you've got electrical machines like hydraulic pumps, some of the electricity that goes to the pump will be lost as internal friction in the machine. Okay, so there's a lot of interest in minimizing the friction losses in machines, because then you'll reduce your fuel usage, either your gasoline or your diesel or your electricity. So if you can reduce friction internally in the machines, that can have a big effect on both the fuel usage and obviously the CO2 emissions. So if you look back at cars from, say, the 60s or 70s, they often typically had a fuel consumption of about 30 miles per gallon. Nowadays, most new cars are more like 50 miles a gallon. And that there's been a lot of changes. That's not just down to the lubricants, of course. It's It's down to a lot of design changes in the car. But the car designers are trying to get the efficiency of the engines higher, and they're trying to reduce the friction losses. So there's a lot going on, but the lubricant also is a focus of attention, because in the past, in the 60s, 70s, or even in the 90s, we used to use much higher viscosity lubricants than we use today. And certainly since the 1990s onwards, there's been a focus on how we can adjust the lubricant to reduce the friction losses.
Yeah, that's really interesting. So the preference, I think, what Elon Musk is the one who says that the best part is no part, right? And in some respects, that also plays into the frictional relationships inside machines, and it's part of the big driver for moving to EVs too, right? They're just a lot fewer moving parts. Therefore, theoretically, the conversion of energy to the wheels is at much higher efficiency. Obviously, on this particular podcast, we're focused mostly on the impact of lubricants and lubrication. So, if I had to broadly break up lubricants into two areas, I know this is very much an oversimplification, but we've got like fluid films and then boundary films. So if you like, instances where moving parts are completely separated by the base oil versus times when we have metal on metal.
Sure.
So could we talk about the role of lubricants in each of those? Maybe if we start with metal to metal boundary contacts, what are the kinds of things that we can do and some of the levers that we can pull to help reduce that amount of friction?
Sure. Well, most machines primarily are designed to operate in the fluid film regime. So most machines are designed in the normal operating condition to have a full fluid that separates the rough metal surfaces. So that's the aim, really. But obviously, when you first start or stop your machine, you won't have a full fluid film. And there are some components like the valve train where the films are very, very thin. So you got to remember that metal surfaces aren't smooth. They're rough at the micron scale. And typically they've got a statistical distribution of roughness. And the root mean square deviation is often half a micron or a micron, depending on how the components are finished. So you've got effectively, when you've got two moving metal surfaces, they're not flat. They're rough. The top one's rough and the bottom one's rough. So you need a film that's thick enough to separate those rough surfaces. And typically, to do that, the oil film needs to be about 3 times the roughness. So if, say, your roughness of each surface is half a micron, the combined surface roughness is it's going to be more like 0.7 or 0.8 microns of the two surfaces. And then you need about 2 microns to fully separate those surfaces. So if your film is less than that, the metal surfaces can touch each other. And that will cause increased friction and increased wear. So what lubricants manufacturers do, they put in additives that help protect the surfaces under those conditions. So the main additive people put in is an anti-wear additive. And that actually forms a thick film, about 0.2 of microns thick on each surface. And so what happens is, instead of the metal surfaces touching, it's these tribofilms that are rubbing against each other. And the most common anti-wear additive used, certainly in automotive applications, is something called ZDTP. And that forms quite a thick film on each surface. But it's also quite clever in that if the load increases, there are cross links made in the ZDTP film which make the film tougher. So effectively, as the load goes up, this anti-wear film toughens up and gets stronger. And so it's almost like a clever film. As conditions get tougher, it actually gets tougher itself. And so what you're doing when the two rough surfaces are moving against each other, you're not wearing away the metal surfaces, you're wearing away these tribofilms. And there's enough ZDTP sort of in the lubricant that these tribofilms can continuously be regenerated, certainly over the period of an oil drain interval. And so you're continuously wearing away the tribofilm and regenerating it. And that's under these mixed and boundary conditions. Yeah.
Do you mind if I just interrupt quickly there? So one thing that I have heard, right, not being a formulator myself, this could be hearsay, but that you can have, in some ways, too much of a good thing. So
Sure.
that ZDDP is obviously forming these layers which are designed to protect engine components, but overuse or over additization of ZDDP can cause very thick anti-wear
Yeah.
films. And because we don't really have a great degree of control over how these ZDDP films form, that you can have an instance in which you are increasing the effective surface roughness. Is there any truth to that?
Yes and no. I mean, you in the past, people put a lot of ZDTP in because they thought more is better.
Mm.
But ZDTP contains sulfur and phosphorus, and those compounds can affect after treatment devices. So nowadays, the amount you put in is limited. You can't put in as much as you used to be able to do. But you're right. The films that form the thick ZDTP films, it's not so much the roughness of the metal surface it's important. It's the roughness at the top of the tribofilm. And so there has been recent work, in particular published by Imperial College, where they did a detailed analysis of ZDTP film formation in a laboratory tribology rig called the Mini Traction Machine. And in that machine, the metal surfaces are actually very smooth. The roughness is only about 4 nanometers of the metal. But when the films were formed, these tribofilms, the Imperial College group measured the roughness of the tribofilm formed on top of the metal, and that roughness was more like 50 nanometers. So these tribofilms were actually rougher than the metal surfaces they were deposited on. However, most engineering surfaces are considerably rougher than the tribology machine that these tests were done on. And so it's still a bit of an open question. If you form the tribofilms on a rough surface, is the roughness of the tribofilm still 50 nanometers, or is it affected by the roughness of the metal underneath? But it is important to note that it's the roughness of the tribofilm which matters, because those are the bits that are rubbing against each other.
Mm-hmm.
And the other downside of ZDTP is that because it forms a nice, thick, well-adhered film, it takes a lot of energy to shear the film. And so you end up with the film giving you relatively high friction. Mm. So although it does protect the surfaces, the friction is higher than you really want when the metal and metal surfaces are touching. So what people also do is they put in something called a friction modifier. And that reduces the friction compared to when the friction modifier is not used. And these are usually easily shearable films, things like molybdenum disulfide or graphite, for example, or boron nitride. And so these are compounds which effectively have 2-dimensional layers, and they form on top of the rough surfaces, and the layers slide across each other very, very easily. And so you don't have to put much energy in to actually shear these things. So instead of the rough tips being sheared and the friction of that being what you measure, you're actually shearing these thin films on top. And so that reduces the friction coefficient from, if you've got a steel with a ZDTP film on and you're in the mixed and boundary regime, you could well have a friction coefficient of maybe 0.1, 0.12. If you put in a molybdenum friction modifier, you can reduce that to say 0.05 or 0.04, so that you can get a substantial, you can still have the anti-wear protection provided by the anti-wear films, but you can reduce the friction. I mean, the one thing I would say is that the amount of time, I mean, there's lots and lots of testing done of rough metal surfaces and mixed and boundary friction. Most machines only ever spend 10% of their time in this regime at most. So although you do these tests in the lab, they're almost extreme cases, because the number of times that machines actually get into this regime, and that you have to worry, particularly when it's fully boundary, where there's zero film at all, it's a small proportion of the machine's time, or it should be anyway. And as the film gets thicker, you get a transition from no film and full metal to metal contact, or tribofilm to tribofilm contact. As the film thickness increases, you get a mixture then. Some is fluid friction and some is mixed, some is friction between the metal surfaces. And that's when you have this mixed regime. And so obviously then it's not quite as severe when it's boundary. So I think all this work that's being done in the lab is it's clearly very essential, and you're putting additives in to protect these surfaces. But like I say, for most machines, they're not designed to operate in that regime all the time. It's usually a small proportion of their time.
Yep. Well, that's a good segue into kind of full fluid film lubrication, right? Because, like you said, that's where we expect most machines to spend the majority of their time, certainly operating time. I think probably the analogy that most people are familiar with is this ball bearing analogy, right? When the lubricant goes through the contact zone, it's getting squeezed between two loaded surfaces, and all the molecules are trying to slide past each other. And the benefit of synthetics has always been that if you have very orderly, nice and regular sized molecules, that they easily slide past each other, versus lightly refined mineral oil, in which case they all kind of get jammed up. So to what degree is that an oversimplification? And how would you maybe describe, let's say, for example, the energy loss in some of those fluid films?
Well, to some extent, it's a bit of an oversimplification, but it's also a bit of an extreme case, because a ball bearing is actually very heavily loaded, and the oil in a ball bearing is usually under incredibly high pressure. So we step back and look at, say, a journal bearing, for example. In your car, you've got a crankshaft, and the shaft is enclosed within a sort of housing, and there's a very small gap between the two, usually about 50 microns or so, and that's filled with oil. And when that's loaded, you've probably got a film thickness between the moving parts of probably about 5 microns on average, but it could get down as low as 1 micron, so it could get into the mixed regime. So you've got the journal bearings in the machine, you've got the piston rings in the machine, you've got other components. Most of these are lubricated with a thick fluid film, which is not under great pressure. So this alignment doesn't necessarily work as in the same way in a low pressure contact. But what's important is what the viscosity of the fluid is in that contact. So the important property of the fluid is the viscosity. And in the high pressure contacts that you talked about, like the rolling bearing, that is a case where the molecules tend to line up because the shear is high in a high pressure contact, and it tends to align the molecules. And some synthetic lubricants like polyalpha olefins, and some of the group 3 base oils, they basically have less branched hydrocarbons and less naphthenics in. And if you've got a branched hydrocarbon or a naphthenic, it's a bit of a funny shape, and it's not as easy to shear through these contacts. And viscosity is effectively the internal friction of the fluid. It's how easily the molecules flow over each other. So if you've got a mineral oil, which has got a mixture of branched hydrocarbons, it's got some naphthenics in, all of these things are rolling over each other, they will have higher friction than if you have a nice, simple, straight hydrocarbon. So the benefit of the synthetic oils, the polyalpha olefins, the group 3s, is that they're more highly refined, and some of these undesirable components like the branched hydrocarbons and the naphthenics have been removed. And that naturally leads to lower friction at high pressures. Yeah. But the other thing that is important between mineral and synthetic oils is the way that viscosity varies with temperature is slightly different.
We always see that sort of characteristic line between, say, for example, I know it's not a straight line, but you always see that representation of viscosity at 40 C, viscosity at 100 C, right? And the mineral oils have a much steeper decline. So effectively, what you're saying is that to match, let's say, for example, a viscosity at operating temperature, let's say, for example, we're operating at 100 degrees Celsius because it's an internal combustion engine. So a synthetic product would have a lower viscosity at 40 C versus the mineral oil, and then going back to 40.
I think it's probably easier to think of maybe the hydraulic fluids, the ISO grade system. So in the hydraulic system, so in the industrial lubricant space, we use the viscosity at 40 degrees C
Yep.
as the standard. And so if you have two fluids with the same ISO grade, and you match the VK40 value, then the flatter viscosity temperature curve of the synthetic will mean at higher temperatures, it's got a lower viscosity than the mineral oil. Okay. And at lower temperatures, the viscosity of the synthetic is higher than that of the mineral oil. So effectively, you've got a wider temperature operating window. So something like a hydraulic pump, there's a minimum temperature it'll operate at because the viscosity is too thick, and a maximum temperature it can operate at because the viscosity becomes too thin. And so the benefit of the synthetics is you can effectively operate the pump over a wider range, and you can reduce the mechanical losses at higher temperatures because the mechanical losses depend on the viscosity. So if you come back to an engine oil, if we think of a heavy duty vehicle, and we want to match the viscosity at 100 degrees C, we would often choose, say VK 100 to be about 12.5 centistokes for heavy duty diesel engine oil. The synthetic oil has what we call a higher viscosity index. And so when we go from 12.5 centistokes to 100, the viscosity is obviously higher at 40 Celsius, but it's not as high as it would be if it was a mineral oil, which might have a viscosity index of 100 rather than 150. And so what you've matched your viscosity at high temperatures to be correct, to give you the protection you need. But at lower temperatures, the viscosity of the synthetic is lower than it would be if it's a mineral oil. And because you've got a lot of engines operating at low temperatures, they're not always fully warmed up. In that lower temperature operation, when you first start for the first 15, 20 minutes while the engine is warming up, you can get significant energy efficiency benefits from using a synthetic oil.
Yeah. Okay. And so I guess it's like instead of pushing honey around your engine, you're sort of pushing water. Obviously not quite that stark, but that's
the other benefit is at even lower temperatures, if you're down at sort of minus 20 or minus 30, and you're using mineral oil in your engine, it can sometimes be difficult to start the engine because the viscosity of the mineral oil is too high, whereas a synthetic oil will have a much lower viscosity than the mineral oil will have at those low temperatures. And so you'll have easier startability as well, which can be important in some countries.
Yeah. I think that's a good segue as well into the discussion about some of these very low viscosity engine oils. I think GF6B was the first time we saw 0W16.
Sure.
And now we're even talking about 0W12s. And like you said, with the new sort of hybrid era, we're seeing a lot of engines that never really get up to full temperature for an extended period of time. So the big question about a lot of these lubricants is, yes, we can see that lower viscosity means more efficiency. Doesn't that mean that my engine's going to fall apart as we move to 0W12 and 0W8? So, lubricants has always been interesting in that it has to go hand in hand with developments in the technology side as well, right? So what are some of these technologies that are happening on the machine side, which are enabling these ultra low viscosity engine oils? And we're still getting this effectively good durability out of the engine, but with much less fuel consumption.
Sure. Well, first of all, the new oils that are coming in, the engine designers will have to design an engine which is suitable for those oils. So it's the engine designer that says what viscosity grade oils you should use in your engine. So you can't go around and put a 016 in like a 20-year-old engine, which was designed for a 5W30 grade. So you're right. The new engines that are coming along are being designed for these oils. And there's a number of things they can do. Traditionally, the component in an engine which has been most highly loaded and most susceptible to mixed and boundary lubrication is the valve train of the engine. And nowadays, the valve trains use softer springs they're lighter materials. They're not as highly loaded as they used to be in the past. So we go back to the 1990s. There used to be an engine used in the European fuel economy test, the Mercedes-Benz M111, and that had incredibly stiff, heavy springs, and there was an enormous amount of mixed boundary friction in that valve train. But nowadays, they've got lighter components, softer springs, and the conditions aren't quite as tough as they were. Plus, they also have often ceramic or diamond-like carbon coatings rather than metal to metal. So there's been changes in the materials used and the engineering side of it, which makes the conditions not quite as harsh. So you can go, and also in these components, it's more the additives in the oil which protect the component than the viscosity grade. Whereas for the bearings and the piston rings, it is mainly the viscosity which matters. And they've optimized these components so that they can work with these low viscosity oils. The other thing you mentioned was temperature as well. If you can reduce the operating temperature of your engine, then you can use these low viscosity oils because you don't get up to the high temperatures that would make these oils too low viscosity. So a lot of the time we use the high temperature, high shear viscosity measured at 150 degrees centigrade as a measure of the durability of the oil. Or it used to be used as a measure of the durability of the bearing. And so for many years, people didn't go below 3.5 millipascal seconds. And then they realized that, in fact, if you designed your bearings and your piston rings appropriately, you could go to lower viscosities, and that would give you energy efficiency savings. So we went down to 2.9 HTHS viscosity with the 5W30s grades, and now we're down at 0.20s or 0 or 5W20s. We're now down at maybe 2.6 millipascal seconds. And then these newer viscosity grades coming in, these 0.16s, they're trying to lower the high temperature, high shear viscosity still further. And so the other changes that people are making is that they can use these low viscosity oils if they make their components smoother. If the components aren't as rough as they were in the past, you actually need a thinner film to separate them than you would if the components were rougher. So it's a combination of material changes to the roughness, changes to the operating conditions. It's a whole host of things that enable these engine designers to specify these oils as being useful.
Yeah, that's really interesting. So it's kind of like always a dance between, your surface roughness, your film thickness, the durability of the components, how heavily loaded they are, and all these kind of things are always playing together. Maybe to move a little bit towards a discussion that's more catered to the industrial end, right? Yeah. Where obviously there's a lot of discussion on the engine oil side, but on industrial, lubricants have a lot to say, so to speak. We briefly talked about using high viscosity index hydraulic oils to good effect, but there are other areas, as an example with low traction gear oils or refrigeration compressor oils, which are, again, either low energy consumption or they help with low carryover into downstream components. Could you talk a little bit about the impact of lubricants on some of those
Sure.
areas of energy consumption?
Yeah, so in gears, there's less scope for improvement because the efficiency of gears tends to be quite high. So when you've got a fully warmed up gearbox, it could be 90% efficient. So you've only got 10% inefficiency. So usually, if you can get a 1% improvement in efficiency, that's a big deal for gears. So people are definitely looking at changing the lubricant to improve gear efficiency. So you'll go into lower viscosity grades, you'll go into synthetic base oils. Some people have looked at things like polyalkylene glycols, have even lower viscosities at high pressure than polyalpha olefins. So there's a whole range of things people are doing. One of the important things about gears is again, that there's this dilemma between fluid film lubrication. And so you have a film between the gears. It's called an elastohydrodynamic film because the pressures are so high. But you also get occasions where the metal to metal contact occurs. as well in gears. So you've got additives in the gear oil. So you've got combinations. Sometimes it's the fluid film that's separating the surfaces and contributes to friction. Sometimes it's the metal to metal contact. The one thing about gears is ZGTP is not usually used as an anti-wear additive because it's found that if you have high friction at the gear surface, it can lead to micro pitting. So they tend to use anti-wear additives and friction modifiers, which give you lower friction at the surface. And that tends to reduce subsurface stresses and means there's less chance of micro pitting. So ZGTP, which is widely used in engine oils, is not really used that much in gears. You use alternative additives, and you try and make sure the friction is as low as possible at the gear surface to minimize subsurface friction. So there's a lot of work going on to improve the efficiency of gears, but it's a bit more difficult to measure it because, like I say, they're so efficient. One thing that has been done, and it was done in my time at Shell, was that you can easily measure the temperature of the oil in the gearbox. And if you had a gearbox which was lubricated with a mineral oil, and then you move to a synthetic oil, you could often see the gearbox temperature drop by about 5 or 10 degrees centigrade. And because the temperature in the gearbox is only there because of friction, there's no combustion in the gearbox. So if you have the oil heating up, it's entirely due to the internal friction in the gearbox. So if you end up changing the oil and the oil temperature goes down, then it's a sign there's less friction in the gearbox. And it usually also means the oil lasts longer because lower temperature means there's less oxidation. So you can definitely do things in a gearbox with the lubricant, which will improve things. And like I say, although it's difficult to measure the gear efficiency, there's no standard tests available. There are ways you can actually see that the thing is working as it should do.
Yeah. Just to take one step back, I mean, you briefly mentioned polyalkylene glycols.
Sure.
Now, I know they come in all kinds of different flavors, right? You've got the EOPO and sometimes the EOBO, EOPO, all the rest of it. But broadly speaking, with that sort of family of synthetics, what about its structure makes it a low traction fluid?
Yeah, that's a good question, actually. I mean, I think people have tried to understand these pure fluids in the terms of molecular dynamics.
Mm-hmm.
You've almost got to put in the actual structure of the molecule and try and work out what it is that's giving you high traction or low traction. So in the past, the people have published papers on something called Santotrac, which is a notoriously high traction fluid. And naphthenics also give you high traction. And there are some applications where that's good. There are some continuously varying transmissions which don't use belts, but they use metal to metal contacts, and you actually need a high traction fluid for those applications. But for most applications, you would want low traction in terms of low friction. The disadvantage is if you have low traction, you have effectively a low pressure viscosity coefficient, and that means you have a thinner film. So again, there's a bit of a dilemma. You might get lower friction, but the film is also thinner. And if the film is thinner, there's more chance of metal to metal contact. So it's a case of deciding, you need to know pretty accurately what the conditions are in your component. You need to know what the roughness is, and you need to sort of work out where the best point is. The other disadvantage of polyalkylene glycols is they don't mix well with standard oils, and they can remove paint and stuff. So, a lot of people don't like using them because of the other disadvantages of them.
Yeah, they're a devil to have on site. Inevitably, if you have a PAG on site, it will get mixed with something else.
Yes.
It always ends up being a sticky mess.
In the one area that there is, where gears are less efficient, are things like worm gears. There's a lot more sliding in worm gears, and so there's a lot more focus in those applications on optimizing the lubricant to improve the efficiency, because there's a bigger prize to be gained, if you like. There's more to go at. And I think I've seen data with a mineral oil where the worm gear was only 75% efficient, but when you put a synthetic oil in, it went up to almost 85%. You had quite a big increase in efficiency for worm gears. And that's
Yeah.
because the sliding.
Hmm. Yeah, that makes a lot of sense. Um, so one thing that we haven't really addressed would be greases,
Sure.
which are, I feel like greases always get a bit of a raw deal because they are so
Yeah.
prevalent, but they seem to be like the lubricant's poor cousin. They don't get talked about as much. So it would be remiss of me to not talk about greases. Um, I don't see all that much discussion on energy efficient greases, comparisons of different types of thickeners. Even when people talk about, synthetic versus mineral base oils within a grease, no one ever really talks about the impact on energy efficiency. So
Sure.
first question would be, do you think there's a reason for that? Like, are there technical reasons for that? And do you see any research on energy efficient greases and comparing different types?
Yeah, I think one of the reasons is that greases are often used in rolling element bearings, and rolling element bearings have incredibly low friction. So actually measuring the friction is quite complicated. I was involved in a project with the university in Germany in Magdeburg, where they made a rig to measure friction in rolling element bearings. They had about 4 rolling element bearings on the shaft, and they connected the shaft to a flywheel. So they would span this flywheel up with a motor. Then they disconnected the motor and basically timed how long it took for the shaft to stop spinning, and that was a measure of the friction in the bearings. And it could take quite a few minutes for these things to stop spinning. And then the idea was we change the grease to see if it would change the time it took for the shaft to stop spinning. Hopefully it would last longer and there'd be less friction.
It's a clever experimental setup.
So, there are a few details you have to get right because, yeah, I think I'll have to check if that's published, but the friction losses in each bearing were incredibly low. And so you were trying to measure a difference in something that was already low. And it's not just the grease formulation that matters, that it also depended on how the person packed the grease into the bearings. You could get a slight difference in friction if you packed the grease slightly differently. So there's a lot to get right. So I think one of the reasons is it's quite difficult to do the friction measurements on these bearings because the friction is already so low. But there are people who've done work on low noise greases, and because there's a lot of interest in minimizing the noise of machines, particularly on construction sites. If you're in a city, there might be regulations on noise. And so people have looked at reducing noise in greases, and that is thought to be related to how rough the thickener is. So the smoother the thickener, the lower the noise is. And it is thought there are a connection between noise and friction. So if you had a thickener which is sort of like less lumpy, it will have less noise, but it should also have less friction as well. But I think you're right. There's less been done in greases in terms of energy efficiency. There was a recent paper from a guy from Schaeffler, Vasilius Bakalas, where he attempted to calculate the total energy loss of all the rolling element bearings in the world. And he was trying to sort of see how much energy was used by all these bearings and potentially how could that energy be reduced by reducing the size of the bearings or changing the lubricant. But I say, if you want a synthetic grease, all you need to do is change the base oil in the grease from being a mineral oil to a synthetic oil. And that should have the same benefits as a synthetic fluid in that the viscosity varies with temperature in a flatter way. And so you can sort of choose to have the grease operate in a wider temperature range, or you could make the viscosity low at low temperatures. So it stays fluid. So there are benefits. It's whether or not you can measure the benefits and articulate them to the customer as to what they get in terms of these benefits. Does it save them money? If you can demonstrate to customers it saves them money, then there's a good story to tell. But I think traditionally, in terms of energy efficient lubricants, we started with car engines because that was the low hanging fruit. We're now moving more to heavy duty engines. There's also some interest in hydraulics, but I think getting the whole of industrial lubricants, including grease, to think about energy efficiency from the lubricant, it's a journey. And as you get more data from passenger cars, heavy duty hydraulics, you see the benefits of these energy efficient lubricants. Hopefully will persuade people in other industrial lubricant applications to follow suit. I think the other comment I'd make about grease is much of the focus of research recently in grease has been how to remove lithium from greases, because the price of lithium has been going up because of the demand for electric vehicle batteries. So people have been looking at calcium sulfonate greases and other options. So most of the work in greases has been focused on trying to get alternatives to lithium as a sort of short-term measure to address the rising costs. So I think that may be the other reason why there's been less on energy efficient greases.
Yeah, no, it makes a lot of sense. I always like to sort of finish out these episodes with a bit of a discussion about what's coming up. You know, if you can peer into your crystal ball, what would you either like to see in the next few years, or do you even see any kind of nascent technologies that are maybe, you know, on the cusp of breaking out of the research phase into commercialization? Is there anything that you see that is exciting in this area?
Well, I think one of the big trends in lubricants at the moment, people are trying to make lubricants more sustainable. And so there's a big push. There's certainly a lot of people out there looking at bio-based base oils. So the idea is you grow crops, you make you process them and make a base oil out of that. It's sustainable in that you can grow the crops again the year after. And so there's certainly a lot of people interested in bio-based base oils. And you're probably going to see a lot more of these components on the marketplace. And they have different properties from hydrocarbon-based base oils. So trying to understand how to use those in the most effective way. And you might need to change the viscosity grade, for example, or you might need to use different additives with those base oils. But certainly quantifying how sustainable lubricants are is quite interesting. So I've been doing some recent work trying to look at the CO2 emissions of lubricants compared to the fuels used in the machines. And for a car, if you drive 10,000 miles a year, you emit 3 tons of CO2 from burning the fuel. Okay, that's about 1,000 liters of fuel. But if you think about the lubricant, you've only got 4 liters of engine lubricant in there. And the amount of CO2 that's used to make that is about 15 kilograms. So the CO2 for the lubricant is far, far less than the CO2 generated by the fuel. And in fact, to make lubricants more sustainable, the easiest thing to do is increase the oil drain interval. And when you've got the oil at the end of the oil drain interval, if you can recycle the oil, then there's a lot less waste. So in fact, one route to sustainable lubricants may not be to go the bio route, but to actually try and extend the oil drain interval and then recycle the oil after use to make new base oil. So I can see recycled base oils becoming much more prevalent in the marketplace. And the benefits of that is you also don't have to dispose of the used oil. Yeah. So in many countries, the official sort of rate of used oil, you're only recovering about half of it. And not all of that is recycled to base oil. Some of that is simply burnt in the countries which allows that. So the focus on sustainability, people are going to be looking a lot more at how lubricants are made, what their CO2 footprint is, how they're packaged, and how the whole thing can be recycled at the end. And if you think about crude oil, very little of crude oil goes to make a lubricant. Most of it goes to make fuels. So if we move away from combustion engines, there's still plenty of crude oil out there that can be made for lubricants. And if that can be recycled, you've almost got a circular economy. And so I think the whole focus on sustainability and how best to do it, and whether it's the bio route or recycled oil route, that's going to focus a lot of minds in the near term. And I mean, if there are new additives that are coming along, which can give you improvements in terms of anti-wear or friction modifier, I mean, those those will obviously be used if something comes along which is better than what's already there. So, I mean, I think there's a lot of things going on, and you can't always anticipate what will win out. But certainly there's a lot of interest in recycling of used oils, and how that varies from country to country may differ, because different countries have different rules about how they collect used oils. But certainly I think that's going to be a big trend going forward. Which is the best way to make a sustainable lubricant? Is it to go bio, or is it to just recycle used oil and use it again? So,
fascinating. Well, Dr. Taylor, thank you so much for sharing your knowledge. I know I got a lot out of that discussion, so hopefully the audience did too. And we'll have to get you back for a round 2 at some stage.
Okay, thanks a lot. That's a good conversation. Thank you.